ahead to a project that Gerwick is in a joint venture as the designer. It's the #1 priority civil works project that the Army Corps has, the Olmsted Dam on the Ohio River. And we're just pointing out high performance blast furnace slag Tremy concrete here, so it has a lot of workability issues and thermal issues. So first I'll give an introduction to Olmsted Dam so that you have an idea what we're talking about, then we'll go into the concrete properties. And again, I'll just emphasize, I know that not every bit of technology is appropriate to everybody's concern, but at least you know that there's a whole suite of technology here that's applicable. It goes from, it's on the Ohio River, about 17 miles upstream from the confluence of the Mississippi. It goes from Kentucky to Illinois, and it's about a half-mile long. It's a navigation dam, not a water supply dam. It's got Tainer gates, about 600 foot of Tainer gates to regulate the river, and a navigable pass to allow the navigation to go by during high water. And during low water, they put up the navigable pass, and the traffic goes through the twin locks, 1,200 foot long locks that have already been built. So you can see the locks here. They're low level. They go underwater. The water goes up and down about over 30 feet from winter to summer, and the lock does go underwater during high water. And to facilitate construction, it was an environmentally sensitive area, and it would have been difficult to put 3 stages of cellular cofferdams across the river, and it wouldn't have matched their funding stream. Building it using precast concrete elements built on the river bank kept it out of the flood stage and allowed them to stretch out their spending dollars to match the funds that were available. So we built the precast yard here on the riverbank. All this was done by for the Louisville district of the Army Corps. And the contractor elected to use a gantry crane. It's about close to a 6,000 ton gantry crane superlift. It is possible to configure it differently to skid onto the marine skidway, but this felt it was optimal to do it that way. So these precast dams shell segments weigh close up to over 5,000 tons. We have a cradle for a marine skidway. A lot of it goes underwater so that you can launch out the shells at different water stages depending on wherever the river's at. And this super gantry is tall enough to lift up some of the shells and go over the top of others if need be. And there's a lifting frame to provide structural support to the shells as they're lifted, so it's like a strong back, but also it acts as a Tremy placement platform. So all of the Tremy goes down through these legs and through holes through the shell. You can see some reinforcing in it. The Tremy ties in the shell to the pre-driven vertical 2-foot diameter steel piles driven into the bottom of the river. There's a 8.3 Richter scale earthquake requirement here, so a large requirement. After the shell goes down the marine skidway, it gets picked up by this over 5,000 ton capacity gantry crane barge that uses strand jacks to lift up the lifting frame and transport the shells partially submerged to the site where it's set down over the piles. So the piles would be here, they're not shown. There's also a grout mat to provide a good clean interface. It could be cleaned off. And once it's cleaned off, there's some water that's circulated in here to put any suspended material into suspension. Then we start at the lower point, placing Tremy concrete through the legs, and then move up so that we always place concrete in the previously placed concrete until we fill up the shell. They've already placed the stilling basin shell, and I believe that they're starting on the OG or sill shell here this week. This is another project that was comparable. Instead of using a lift-in type of approach, Braddock Dam on the Monongahela River for the Pittsburgh district. Was a float-in type of a shell where they used these maintenance bulkheads to provide a buoyancy, and then they floated over drilled shafts with a pintle type of connection. And they used Tremy concrete in there, and then just to get a seal, and then they went in the dry and placed the rest of the concrete in the dry. Here's another example that uses a fair amount of anti-washout admixture. It was we consulted on 4 jobs like this in Florida, where ships would hit a reef, and the reef is only alive on the surface. So when it's dead on the surface after it's been collided. So they wanted to come up with this dental concrete to repair the cavity so the reef could go on growing and not die away. So we made in precast concrete elements and some rock boulders, and then used anti-washout admixture with the Tremy concrete to have essentially almost a zero slump. No, not a zero slump. Well, it was almost a 12-inch slump concrete. It was self-consolidating concrete. And there was no negative impact on the surrounding fish or the lobsters that were down in there. So the anti-washout admixture stops the cement particles from going off into the water, making it alkaline. So for those who don't know, Tremy concrete is placed through Tremy pipes to separate the fresh concrete from the water, and then you form a seal, so you're always placing concrete into previously placed concrete, so it's not mixing with the water. Some advantages are you don't have to have a cofferdam, but you often use Tremy concrete to seal a cofferdam as well. But in this case for Olmsted, we don't even have a cofferdam. And it's an efficient way to place large volumes of concrete. Disadvantages, you have low accessibility to check the placement, so you need to do a lot of quality control in advance. There are sonic methods for checking and coring and other methods. You don't normally consolidate the concrete. We've done studies where there are ways to consolidate it underwater, but if you do start agitating, it can start to promote mixing with the water. And you want to have something that's self-compacting, but of course with buoyancy, it doesn't flow out the same way because it's supported by the water. So of course, there's risks of honeycombs. There's concerns about latents. Latents is when a little bit of the fresh concrete mixes with the water, and there's a little bit of surface to the concrete, so the concrete's better down below the surface. There's concern about washout, and there's particularly heat generation here, so we use a large quantity of blast furnace slag for a large concrete placement. So we had good flowability, was self-consolidating, low heat, and self-retarding. We used an anti-washout admixture, which is something you could think of like salad dressing. It's an admixture. It makes it thicker, so it's instead of running like water, it's more like salad dressing. So this is we had a 10-inch slump on the concrete for Olmsted Dam, rather than like what we used in Florida. And we also, there's a slump flow table test that you measure the diameter of it as it flows out, which is another measure of its consistency. But as you see, it builds up around the bottom of the Tremy pipe, and it builds up a little bit of driving head to push it out. It moves out like a series of landslides. It builds up enough head, overcomes the shear strength of the fresh concrete, and slides out. And you build up another pile here as the concrete comes out, and it slides out and moves out laterally. So it's always moving concrete through the previously placed fresh concrete, and you always keep lifting up the pipe as you get up to the top, so that you're not placing through concrete that might be setting towards the bottom. So there's a techniques associated with this. This just shows an anti-washout a test for measuring washout that the Army Corps had adopted. Also, when you put in the anti-washout admixture, it also decreases bleeding, so there's better adhesion with the bars, reinforcing steel. There's less top bar effect of that. We, of course, monitored the compressive strengths. These were just the design properties. On this particular job, we had an initial set time between 6 to 24 hours. We wanted to keep it workable while it's being placed underwater. So here was the strength gain with time. We had it heavily retarded here with a lot of admixtures, so it took a while for it to reach set. And then you can see within a few hours afterwards that we were up exceeding our design strength, because you have to put an extra amount of cementitious material into the Tremy concrete to get the workability. So the strength is almost a byproduct. Reaching the design strength, as you see, was achieved within 1 day. Here is a Tremy concrete mix design. You can see the blast furnace slag. We used coarse aggregate and fine aggregate. Some of the key features here, we also used limestone powder. That's a little bit unusual, but it does have a little bit of reaction with the cement. And also reduces the heat. We had fly ash as well and silica fume. Here's the high range water reducer, the low range water reducer to extend the workability life. And here's the anti-washout admixture. So this is a photograph of the coarse and the lightweight, no, not the lightweight, the standard coarse. Just gives you an idea of the type of meshing we had. It's important when you do a mixed design, you have to always observe the fundamentals. You shouldn't just use anti-washout admixture to solve your problems, or use a high-range water reducer to try to ensure workability. You have to have a good gradation of your aggregate to try to keep your cement content under control. This does show that of the cementitious material, half of it was granulated blast furnace slag, only 14% was cement, 10% fly ash, 23% limestone powder, and 4% silica fume. So we only had 14% of a material that was causing a carbon footprint. All the rest of this is either a byproduct, essentially. But although it is a green mix, the main purpose of this was to control heat of hydration for a massive pour. So here's the granulated blast furnace slag. It gives you the unit weight. It's actually lighter than cement, so it can have an advantage that way. Whereas weight's important. If nothing else, this was a seismic zone. By having a lower density, you had a little bit less seismic demand. This does show the rate of heat of hydration for a typical slag. So without any slag, you'd have a lot of heat, more heat, and it would come earlier. With a 65% slag, blast furnace slag, it would be less production of calories. Here's the representative heat generation with all cement. You have a higher heat of hydration. With a slag type of a concrete, you have less heat of hydration. So it's you can put in more slag than you can fly ash, so you can get a lower thermal footprint here. We also used type 2 cement. It had better resistance to sulfate and hydration. On our mixed design, I believe we had a 3.8 water cement ratio. So this just gives you some of the background on fly ash. It comes from burning coal, and then they collect the fly ash going up the flue, and then they have to process it a little bit. But it also reduces the heat of hydration. It can reduce the rate of slump loss, so you can have a longer workability life. It can improve the pumpability, decrease the permeability by increasing the paste volume and reduce bleeding. I guess this is a result of some of this hydration going on. So this just gives you the time since placement with the heat rise by using up to 30% fly ash, which is about close to the. You can go higher than that, but you get reduced strength gain, as we showed here with our